which is also a squared plus b squared. So yes, indeed, this triangle satisfies the vectors of 0, namely this quadrant plus this quadrant equals that quadrant. That's telling us geometrically that that is a perpendicularity there, or a rectangle. Now I'm going to give you a novel but important definition. This is something that you don't see anywhere else. We're going to talk about the cross product of two planar vectors, two vectors in the plane. Cross product. Okay, here it is. If v equals the vector AB, and w equals the vector CD, then we're going to define the cross product E cross W to be equal to, well, that same quantity, that same determinant that we've been studying over and over, AD minus BC. In other words, the area of the parallelogram formed by V and W in that order. We're going to find the area of V, precise. Now, this will take getting used to for some people because if you're taking engineering courses, you're familiar with the cross product in the context of vectors in three-dimensional space. You know that you get two vectors in three-dimensional space, and the cross product is the third vector that's perpendicular to the two vectors that you have. Okay. We are not working in three-dimensional space here. Our vectors are vectors in the plane. And so this cross product is different, but still very closely related to the more familiar cross product in three dimensions. Okay. So I got a baby version of that, think about it that way. So the cross product of two vectors is a number. In fact, it's just the area of the parallelogram spanned by those two vectors. Okay, now I'm going to leave you with a little bit of exercise to check some basic but fundamental things. That if you need to change the order of the vectors, then the cross product changes sign. That if we take a vector cross itself, we get 0, the number 0. And that the cross product is linear in an obvious way. That if you take V1 plus V2 cross W, then that's the same as V1 cross W plus V2 cross W. And then if we multiply by some scalar lambda, lambda V times W cross W is the same as lambda times V cross W. And that's also the same as V cross lambda times W. So these are important properties of the cross product. You might wonder what about the distributivity in the other direction. Well, if you combine this one with the first one, then you can see that the distributivity also applies to the second variable as well, so there's nothing special about that. Okay, so this little exercise, make sure that you check that this very simple but novel definition of the cross product of two vectors has these nice linear, but sort of skew symmetric properties. And now let us connect the determinant via this cross product with our fundamental measurable quantity of quadrants. Okay, the result is the following here. That if V is a planar vector, say AB, then the quadrants of V is the same as the cross product of V with V super V. So V super V is that perpendicular rotation of the vector V. Okay, well, let's check that. So we know what the quadrants of the vector V is. It's just the sum of the squares of its components. It's A squared plus B squared. And what is this thing? Well, there's the vector V, and there is the vector V super V. There's the perpendicular rotation of V. And if you take the cross product of these two vectors, what do we get? Well, it's AD minus BC, so it's the product of the outer ones, which is A squared, minus the product of the inner ones, which will give us A minus B squared, or A plus B squared. So yes, indeed, the quadrants of AD is equal to the cross product between the vector V and its perpendicular rotation. In that order, here's the vector V, and there's the vector second, that rotated vector. So in determinant form, what we're doing is we're noting that the quadrants of a vector could be written as a determinant. It's the determinant of the matrix that you get by writing down the vector together with its perpendicular rotated vector. And that little geometric matrix is determinant. It's just the quadrants of the vector V that we're starting with. In the next video, I want to talk about squared, which is the more novel aspect of rational trigonometry, replace an angle, and how that is also intimately connected with the notion of determinant in the way that we've seen before, but which also has interesting manifestations in other geometry. So I'll remind you a little bit about chromogeometry and not just the but also the red and the green. The geometry is a uniform understanding of squared and the relation with determinant. So we'll look for that. I've got more. Thanks for listening. Welcome to Australia. This is Bruce Hewlett, right here. Look forward to this chat. So I want to bring up a couple of so from outside the world of mathematics, most people think that the conclusions in the world of math are all logically certain. Beginning to end, A to Z. So with simple primitive, here's your mathematical reasoning and conclusion necessary law. And so the idea of being skeptical of conclusions in mathematics looks like mathematics will say exactly. You think that the correct way to see the area of mathematics that really is this area of completely airtight logic. So we're going to skepticism about some more philosophical questions. Well, I think that's pretty safe to say that it's not as safe. Historically, there have always been contentious aspects of mathematics, and the logical structure has often been challenged and no friends or interpretations have been around. But it's important to make the distinction between, let's say, foundational issues and more advanced mathematics. Typically, what happens is that you apply energy to a logical structure and rigor of more advanced arguments, and they're looked at very carefully, and you have thought about very deeply, and mathematicians are looking at the figures showing. So at these higher levels, there's often a lot of really solid and what you may consider personal logic. But the difficulties are often about more foundational issues. So at the bottom, where especially for studying foundations of the subject, there things are not so clear. There's more interpretation and ambiguity possible. So it's really things that are high school, in primary school, and sometimes in the first year, at the graduate level, and those areas where they use conditions so on. Yes, problems can certainly arise. I think they certainly have. I think modern mathematics has severe foundational challenges, and I think we're seeing a time where they're relating the reversals and how we think about foundations. So if it's philosophy, when I think about foundational issues, I think it's really important. If the foundation's wrong, then you're going to do these. It's harder to go out on the theory, you build that foundation. If that foundation system, which is largely independent of the so-called axioms. So Marx had theory that built up in the 20th century. So those axioms, that framework, is really some kind of formal justification that people point to, but it's not really something that's used on a daily basis. So most mathematicians like myself are not even really consciously aware of all of the axioms. I'm certainly don't use them in our daily work, so it's not the case. We use axiom 5, and then the next couple of we use axiom 7, as you might imagine. So, and it's really important to understand that the essential difficulties with mathematics, although they're reflected these days in the discussion of infinities, so are really about something else. Okay? The infinities come up because of our attempts to clarify the nature of the continuum. So it's really the continuum which is at the heart of the problem. And there we have a really serious problem that goes back historically a long ways, in which there really is contention. There really has been a lot of debate back and forth, and that's really where the fundamental problems reside. So, what is that? Well, that's a very difficult question. So, if you go back to Euclid, if you go back to Euler, if you go back to Newton, they would have had a very physical approach to that question. So their understanding of continuum would be based on a physical intuition about the space in which we actually live. So Euclid was built, you have to remember that Euclid was built by for mathematics for several thousand years. People studied mathematics. Euclid's geometry is firmly based on understanding of the geometry of physical space, the geometry of the plane. He's concerned about drawing lines, drawing people, making sand, drawing circles. What you get with various constructions and make various arguments about physical space. Now, what was happening is that in the 17th century, the European mathematicians discovered an alternate way of thinking about geometry, and that was really the transformative point. And it was also a place where some of the difficulties of Euclid now started becoming clear. So Euclid does not adopt coordinates, but in the 15th century, from Descartes and people like this, started thinking about geometry in a more Cartesian, in a more coordinate kind of framework. And this allowed us to really get a completely different view of what the actual fundamental basis of space is. So we move to now a position where space itself is encoded by essentially antuples, or let's say pairs, pairs of numbers. So our conception of space becomes subordinate to the conception of the number system that's available to us. And so the problems of the foundations of geometry, which you could have largely been able to avoid, these the points of points and points of lines, and everybody had to deal with the number. So those are the were displays by a more accurate understanding of what a point is in terms of pairs of numbers, what a line is in terms of equation, and so on. So we were able to make this shift where the foundational problems started to be associated with everything. So the question was, what is our number system and how does that work? And the problem is that people started investigating that deeper and deeper as the centuries were passing. They had to start probing more and more carefully into what exactly the number system really was. So what do we mean when we talk about number, right? But turns out it's a very subtle and difficult point, and it's really, it really came to a head in the 19th century when people really tried to begin to call real numbers. And it's that attempt to try to establish real numbers, which is really the core of the most foundational problems that we currently have. Okay, so let's go a little bit deeper into that. When you say there are foundational problems with understanding real numbers, first of all, what do you mean by a real number? And isn't that have a precise definition in terms of what the standard mathematical orthodox answer would be? Okay, here's the question, like what exactly is a real number? It's not an easy question to answer because there are actually several competing different theories. But it's probably good to orient your viewers with the initial position that the kind of numbers is the one that everyone is familiar with. It's very solid kind of rational numbers, otherwise fractions. So we all learn fractions in primary school, comfortable with arithmetic. And then in the modern world, we have this alternate system where we have floating point numbers. That's what our computers largely use. Where we have decimal numbers, 8 to 8 digits, or 8 to 16, or something later. And our computers work in this framework of floating point numbers. fine. But it turns out to have a really big advantage that when he wasn't fine, by definition, the multiplication is actually relatively easy to do in that context. The problem is that even though in these two cases it's relatively easy to specify those steps using the addition is whether a rational number is squared, bigger than 2, or less than 2, or negative margin. But if you have a general real number, then getting hold of that data itself is a process that requires an infinite amount of work. Now, if you want to do, if you want to create this summary for pi, you would have to first get a sequence of negative intervals that surround pi that sort of converge towards it, and use that sequence to successfully take more and more infinite quantities of rational numbers. So, the second type of approach appears to put real numbers on a theoretical foundation. Now, real numbers are sets, or pairs of sets of rational numbers. But possibly, effectively, it doesn't actually indicate the hardware having to involve the process or actually doing this much. So it's something that is available front end allows you to make real numbers using the prior theory of physics. And that's actually the reason, that's the core reason why that story is so important to actually justify creation of real numbers using this particular system of ideas that you have. Okay, so let's get into the story. There are some opportunities that emerge from thinking of real questions in our world.